Yes, welcome to our channel of Sciences and Mathematics. Today we are going to look at a sample question on the board, and this question specifically stems from the topic of chemical kinetics, and we are going to work out and see which, of course, it has been mentioned to be in a second order kinetics. We're going to work out and try to see how we're going to be able to solve a problem in second order kinetics and questions of a similar order. So in this case, welcome. And we'll start first by trying to look at some of the concepts that we have learned about chemical kinetics. From the start, we said that we can be able to measure the rate of a reaction by trying to use the concept or measure the concentration of reacting species and the products by trying to look at the different rates of reactions. This is basically because in our discussion about chemical kinetics, introduction to chemical kinetics, we say that the only way in which we can be able to measure the speed of a reaction is measuring the concentration of the reacting species and the product over time. So in this case, we're going to look at a second order reaction kinetics, whereby we're going to use the equation that I've posted on the board, and I'm going to read it. The gas phase nitrogen trioxide forms those products and obeys second order kinetics. At a temperature of 20 degrees centigrade, an initial concentration of nitrogen trioxide is 0.05 moles per decimeter cubed. The concentration after 60 minutes is 0.358 moles per liter. So the moles per liter and decimeter cubed are just about the same. Assuming that the reverse reaction is negligible, find the value of the forward rate constant. So that is the question that we're going to use and try to figure out how we can be able to go about in finding the value of the forward rate constant. Now, from the general information on chemical kinetics that we have discussed in one of our videos, we said that the concentration of the rate of the speed of a chemical reaction can be measured using the concentration, and this specifically is concentration over time, which is given as rate, and therefore this rate is given as K A N, whereby the initials in the square brackets refers to the concentration, and the K refers to the rate constant, whereas N refers to the order kinetics of that specific reaction. So therefore, this particular reaction can as well be represented, or the rate can be represented as a change in concentration over time. So therefore, I can write a second equation which gives the change in concentration of this substance over time as that one. Now, in this case, of course, we can see that the two equations relate to the concept of change. I mean, the concept of rate. Therefore, I can equate the first one and say that K, concentration of AN, is equivalent to A, the change in A over change in T. And I've given this one negative. Now, this negative implies that the concentration is decreasing for the reactants, is decreasing with the time. And therefore, in that case, for a second order kinetics that I've given, we're going to see that there's going to be a different, of course, a representation for this kind of an equation from a general to a specific one. So therefore, for a second order, I'm going to give it as rate equals K A 2, which is squared for second order. So in this case, as the reaction for a second order is when the rate is proportional to the square of the concentration of A, which is given as the equation I've written on the board. So in this case, of course, we are going to have this general representation given an equation as such. This is the concentration of A for second order, can be given generally as the change in the concentration with respect to time, given as such. So therefore, now for trying to find out how we can be able to find a general representation for this particular equation, we're going to interpret this set of an equation, and this is for 1, 2. So let me give you this one 3. So we are going to integrate equation 3 in order for us to find a general representation in which we can be able to do maybe some kind of analysis on the second order kinetics which we are required to use in that set of equation. So for that, for this case, I'm going to do an integration for this. So I'm going to do a rearrangement and integration for this. So I'm going to have the integral from 0 to a specific time. There was change in time from so after 60 minutes. So that's a change in time that is being experienced in that. So I'm going to deduct that information from there, but first we're going to find the equation to represent that. So I'm going to have change in concentration of A over squared. I've just done a rearrangement for that. This one, I've divided both sides for this in order to get this set of an equation, and this dt have been multiplied at the other side in order to get the integral of 0 to t k dt. So this is a rearrangement, and in order to form try to find out the integral of that. So this one is going to give me a general representation for 1 over the concentration of A from 0 to t. So that is the integral of that, which is going to be equivalent to kt. So basically this second set is a representation of this. You can just write that representation of this first set of 1, 2 equations giving that one. So if you try to factor out for t in that integral, I'll find this one will give me the concentration at t minus 1 over the concentration at 0, which is going to give me kt. So this is 1 over. So therefore the representation for this specific equation is going to give me a way in which I'm going to find the concentration at a specific time t, the initial concentration, and then the time that is taken. And from this I can be able to calculate the reaction rate constant. So therefore I'm going to just do away with this and leave this equation since it's the one that we are going to apply in trying to find a solution to our problem set. So I'm going to write it over here. So therefore, for a second order reaction, we're going to have the concentration at T minus 1 over the concentration in A equals Kt. So if you try to look at this equation, it is forming the equation of which is analogous to the equation of a straight line. If you try to do a rearrangement for this, we'll have 1 over the concentration of T is equals Kt plus 1 over the concentration, the initial concentration. So a plot of a graph of 1 over the concentration of A against time is going to give me a plot of that nature. And this is generally for second order reaction rates, whereby I'm going to get these are positive slopes. So therefore, the rate constant is going to be a slope, of course, which is going to be a positive value. So in this case, this is how we represent the equation for the second order reaction rate, and therefore this is going to be our basis for trying to find out how we can calculate the reaction, the value of the forward rate constant. So if I try to equate this one, as I said, for the equation of a straight line, I'm going to have general representation for y is equals mx plus c. So therefore implying that the y-intercept is going to form, or to give the initial concentration of this specific solution, or the inverse of the concentration of this solution, whereas the slope of this graph is going to give us the value of the forward rate constant, which of course is going to be from this equation m. It's going to be the gradient for that case. So that one understood, I'll just take out this part of the board and just try to give still that general representation for y 1 over the root of a, the concentration of A at T is equals KT plus 1 over the concentration of A that is initial. So, and then I've said this is y is equals mx plus c. So therefore, let's try to extract the information from this so that we can use it in our calculation. So the gas phase nitrogen obeys second order kinetics. So this is the equation we're going to use. At a temperature 20 degrees centigrade, an initial concentration of, so we have been given that one, initial concentration of nitrogen is 0.05 moles per decimeter cubed. The concentration after 60 minutes, so change in time or t is equals 60 minutes, is, so the concentration after that time, after t minutes, after t seconds or t minutes, is going to be 0.0358 moles per liter. Assuming that the reverse reaction is negligible, find the value of the forward rate constant. So we are being requested to find the value of K, which is a slope as we said. So therefore we are just going to substitute this information in our equation by just maybe trying to still do a rearrangement and write 1 over the concentration of A at T minus 1 over the concentration of A initial is equals KT. So doing a substitution for that, this is 1 over the concentration at T 0.0358 minus 1 over 0.05 is equals KT. So T time in standard units is seconds, so therefore we're going to convert these 60 minutes into seconds. So finding this one, just do a rearrangement of that and find that K is equals 1 over 0.0358 minus 1 over 0.05, and then times 1 over this conversion into seconds is going to give us that. So because of space, the value for K is going to be 2.2 times 10 negative 3 moles per decimeter cubed. It's equivalent to per liter per second. So in this case, this is how we're going to use this information that we have extracted from the sentence in order to calculate the value of the forward rate constant, given the information that we have deducted from the second order reaction rate, the general information, and of course the equation that we have already used in order to cater for that. So in that case, that is how we are going to work with the second order reaction rates and other rates, of course, that we have discussed in our introduction to chemical kinetics. So for that, that is it for today. Thank you guys. Bye. God bless.